I propose that we now study the performances of the different approaches that we have studied so far. So as a reminder, we have seen three different approaches. There was the n-queens checker, that is the generate and filter approach. There was the n-queens prune, that is trying to prune the search as soon as we detect a violation on the prefix of decisions. And then we have the n-queens TinyCSP that was using the TinyCSP solver that we have designed using the variables, the fixed point, and all the ingredients of a constraint programming solver. So in terms of metrics, we might be interested in to measure two different metrics. First, the number of nodes. If you measure the number of nodes, that will show you how large the search space might be. And finally, we have the time. And that's really complementary because you might have a small search tree, but you might spend much more time exploring this search tree because you spend a lot of time inside each node of the search tree. So for the first approach, the generate and filter approach called n-queens checker, implemented in n-queens checker class, we see that for 8 queens, it's quite trivial. It takes a few milliseconds, so less than 1 second. But as soon as you reach 9 and even 10, it becomes quite impractical, right? You take already more than 100 seconds for 10 queens. And so the reason is that you generate a lot of nodes, and you need to filter most of them. So that is a lot of time wasted just by trying to generate all these permutations that you need to filter. The n-queens prune, trying to prune as soon as we detect a violation on the prefix of decisions, is really scalable. You can reach easily 15 queens, so that's much larger. And so you will shift the exponential behavior on that n-queens problem. It takes less than 30 seconds to explore more than 100 millions of nodes and generate more than 2 million of solutions for the 15 queens problem. So that's really scalable, much more scalable than the previous approach. But of course, you see that also it's raising quite quickly, and probably that the 16 queens problem will take way longer than 30 seconds. For the n-queens TinyCSP, that's slower than the previous approach. It's about 10 times slower than the previous approach. And but still, we managed to solve the problem also for 15 queens problem. It's just that we spend much more time in each node. And let's identify what are the sources of inefficiency for this TinyCSP approach. We might use a tool such as Visual VM, a profiler tool, and what we will observe is that the memory is raising a lot and declining a lot. That's because of the garbage collection of Java. And if I analyze the methods a little bit more closely, you see that we spend a lot of time in the fixed point algorithm, and of course, as a consequence, in the propagate method of the not equal class. And we also spend a bit of time backupping and restoring the domains. So how can we improve the fixed points behavior? Well, the fixed point, the way it's implemented in our TinyCSP solver, it was executing all the constraints of your problem as soon as you detect that one constraint was able to prune something. So if you're able to prune something, then you will execute all the constraints one at a time. Okay, that's represented here, but that's also represented here. You apply here the propagation algorithm of all the constraints, okay, one at a time. You measure the new domains, and if you detect that one of the domains has changed, then you iterate one more time over all the constraints. So that's pretty inefficient. And an idea that we might come up with is that if one domain of a variable involved in a constraint didn't change, probably it's not such a good idea to execute that constraint again. And so if we take advantage of that idea, we can come up with a new filtering fixed point algorithm that will do that exactly. But we need one additional data structure that will be the propagation queue. The propagation queue, denoted by Q here, is all the constraints that still need to be executed, that still needs to be propagated. As long as the queue is not empty, you pick one constraint in that queue, that's the constraint C, and you will apply the filtering algorithm of that constraint. As a consequence, you get a new domain that is shrinked, and then you can collect all the variables that have at least all the variables that have the domain that has changed, that was shrinked. And then you will only enqueue the constraints involving at least one constraint that has one variable that has changed. Okay, because there is no point adding to the propagation queue one constraint that involves constraints that didn't change in terms of domains. Okay, and so with this idea, you have a much more fine-grained filtering of the propagation queue, because you will only execute the constraint when you think that it is worth executing them. Because if the domain didn't change, then the propagation algorithm will not be able to remove additional values. And so in the next part, of this course, we will study more fine-grained mechanism to execute the fixed point algorithm using the propagation QID that we have seen just before in the pseudocode. We will also avoid creating clones of the domains and use more efficient data structure for implementing and restoring the domains on backtrack. We will implement a very generic search that can easily implement complex branching decisions and also take into account complex branching heuristics. That's the program for the next part.